Hello everyone, I'm Chiocca, a second-year PhD student of Industrial Engineering at the University of Pisa. In this video, I present a recent research project I work on with my research group. This is about the residual stress assessment of a tube-to-plate welded joint. Specifically, in this case, the presentation focuses on the numerical models implemented in ANSYS software to simulate the deposition process of the weld seam. Generally speaking, residual stresses, and in particular tensile residual stresses, if not intentionally introduced, can reduce the structural integrity of a component in different ways. They can decrease the buckling resistance, the fatigue life, or the static strength of a component, as well as give rise to stress corrosion issues. For these reasons, the following work is intended to investigate the residual stresses in a welded specimen. The studied specimen was obtained through MIG arc welding of a tube and a plate, both made of S355JR structural steel. The welding, or a cross-section of the welding of relevance for our work, is highlighted in this figure. First of all, I start by explaining the experimental activity that I was carrying on. The idea behind was to get relaxed strains data to compare with numerical results in order to assess the simulation methods. The relaxed strains derive from gathering strain data through the use of strain gauges during an incremental material cutting process. This material removal was performed on the back of the plate, opposite to the weld seam. The strain gauges were placed nearby the weld seam at different radial and angular coordinates as shown in the figure here, where Rx is the distance between the weld toe and the strain gauge, while theta is the angular coordinate initialized at the welding starting point. The incremental cutting process was performed starting from the back of the plate. Two holes were drilled. The first one, that you can see in dark gray, was a through the thickness hole of 42 mm, while the second one, highlighted in light orange, was a 100 mm in diameter, generated using 5 mm incremental steps. The stepping process, which was used in generating the holes, has been designed to get relaxed strain data at different depth coordinates. Overall, the relaxed strain is a function of the strain gauge position on the surface, in particular the radial and angular coordinates, besides the depth and the diameter of the hole. These data were then used for comparison purpose and for verifying the results of numerical simulations. The following session deals with the numerical simulation and the assumptions underlying it. To simulate a welding process, a thermal structural simulation was made. An uncoupled formulation was used to describe the welding process, as the displacement obtained during welding are limited and have negligible influence on the thermal distribution. This kind of formulation is so acceptable in this context. First of all, the welding process was replicated from a thermodynamic point of view by calculating temperature variation over time. The welding process was then reproduced from a mechanical point of view through a structural simulation. In this case, the load was obtained as a binary time-temperature data file resulting from the thermal simulation previously solved. At the end of the structural simulation, we were able to collect the results of residual stresses and strains all over the specimen. A third step consists in simulating the material removal process on the bottom of the plate. This process consists of sequential deactivation of some elements. For instance, no load input was given in this case, but the structural simulation results previously acquired were used as an initial condition. It is worth noting that to solve correctly all the passages, a consistent mesh design was required. The mesh structure has to be the same all over the 3-step simulation. Furthermore, a correct mesh structure was required to reproduce the cutting process through the bird and depth method by designing the correct hole geometry upstream. The studied finite element analysis employed a 3D model with temperature-dependent thermal and structural material properties. From a thermal point of view, the temperature-dependent material properties are thermal conductivity and heat capacity, while the heat convection and emissivity were considered constant. Instead, from a structural point of view, an elastic plastic material model was used, through temperature-dependent Young's modulus, yield strength, and hardening rule coefficients. Furthermore, a thermal expansion factor was introduced to calculate stress and strain based on nodal temperature results. All the material properties were taken from recent literature. The thermal analysis is explained firstly. To simulate the thermal load deriving from the welding process, a constant initial temperature method was implemented. The thermal process was initialized, activating a volume of elements at a starting temperature Ti, where Ti is the only parameter this method needs to work properly. The value of Ti was set at 8500 Kelvin, and it has been obtained by comparing the numerically and experimentally derived temperature around the weld bead. Specifically, Ti does not represent the melting temperature of the base metal or a characteristic temperature. Instead, this is a simply fictitious parameter that includes all the features that have been left out because of the simplification assumed in this method. The volume set of active elements were sequentially activated to simulate the welding process using the element birth and depth technique. The sequential activation of the elements set generates a temperature field as described in this figure. For the sake of clarity, all the elements with a temperature higher than the melting temperature have been highlighted to obtain a qualitative profile of the melted pool. Now, the second step of the simulation, the structural part, is described. The use of a constant initial temperature method in the thermal simulation poorly matched the classic approach of a sequential activation of all the elements belonging to the previously used element set in the thermal analysis. For this reason, a more representative simulation of the welding process was implemented in this case. From a structural point of view, two different methods were used and compared. The first one can be considered a standard approach. According to this method, the nodal temperature resulting from the thermal simulation is applied to the nodes according to the correct time sequence given by the welding process. At the same time, the elements belonging to the weld seam volume set, whose position and size depend on the actual simulation time, are activated. The second method, identified as representative welding process, can be considered as an improvement of the other one. In this case, a correlation between element activation and element temperature is added. From the figure, it is possible to identify a sequential activation of the element with a temperature lower than the melting point. The result thus obtained represents what is expected from the solidification of a pool of molten metal during the welding process, and it is likely to better reproduce the stiffness contribution of the seam weld. In the slide, the difference between them can be graphically noted. In the first case, all the elements are activated simultaneously. This leads to a sequential cooling of all the elements belonging to a selected section. In the second case, elements activation is gradual, even within the same section, and better represents the correct solidification. So, this represents better the solidification of the material and consequently the stiffness of the joint. This graphical flowchart briefly describes the representative welding process at the generic simulation time Ti. I will start describing the flowchart from this point. First of all, the elements belonging to the weld bead are selected, part of which is active and remains inactive, depending on the actual simulation time considered. Afterwards, only some of these elements are reselected, whose position is a function of the simulation time. To this regard, it is necessary to select a portion of a weld seam's elements circumferentially large enough to contain the entire interface area between molten and solidified material. This requirement is essential to activate all the elements in the right sequence and not to leave some of them deactivated behind. All the elements thus selected are activated to update the solidified material volume. Instead, concerning the molten material, the update is done detecting all nodes with a thermal load given by the nodal temperature, greater than the melting point. At this point, the elements belonging to the previously selected nodal set are then deactivated to obtain the correct melting pool shape. Finally, all the components elements are selected and the whole model is solved. The simulation time is then increased of 1 unit and the next iteration is performed. As a final part of the presentation, the results of the simulation and experimental activity are discussed. Here, the results of relaxed radial strain are shown over the distance from the weld toe for 2 different cutting depths, specifically 10 mm and 15 mm. The numerical results derived from the use of both numerical methods mentioned previously are here shown. Specifically, in orange, the RVP, so the representative welding process, and in blue the classic method. Besides, experimental results are shown for 3 different radial distances of the strain gauges, 6.5, 9 and 13 mm. For all the cases, a range has been identified in the results, both for the numerical and experimental results, collecting the relaxed radial strain data over the hoop coordinate between 0 and 360 degrees. This range, obtained in both experimental and numerical results, shows the presence of a strong hoop asymmetry in the results. For this reason, it is important to describe the process through a 3-dimensional numerical model. Both methods have comparable behavior during the zero strain convergence phase of the curves, that is this part and this part. However, the higher strain gradient of the representative welding process in the surrounding area of the weld toe is what mainly differentiates the methods and brings the RVP closer to the experimental data. So, it's this part and this part, closer to the weld seam. Since the representative welding process gives fairly better results compared to the classic one, only this will be accounted for in the following. Another important result is the relaxed radial strain as a function of the circumferential coordinate. The experimental data are displayed for the radial distance of 6.5 mm for 2 different cutting depths, 10 mm in orange and 15 mm in blue. To consider a radial placement variability in the strain gauge, a dispersion range has been numerically calculated for a placement variance of 1.5 mm relative to the reference radial quota of 6.5 mm. So, this range can be seen in this data. The strains for both experimental and numerical results have not a constant distribution over the angle theta. For instance, the highest strain values are generally found in the proximity of the welding starting point, so for theta equal to 0 or theta equal to 360 degrees. Again, the asymmetric distribution of results in both numerical and experimental data is quite evident. In this case, the scatter between numerical and experimental results is larger with respect to the case shown before, since the dispersion in strain gauge measurements varies considerably when the hoop direction is considered rather than the radial one. Another interesting way to look at the strong asymmetry of the welding process is to consider the residual stress field both for radial and hoop coordinates. These graphs show the stress trend at the end of the welding process on the plate surface, so before the incremental drilling process. The results of radial and hoop stress are shown, starting from the weld toe until the end of the plate. It is clearly visible a drop in both radial and hoop stresses near theta equal to 0. This is precisely the area affected by the double thermal welding cycle, where the welding process begins and ends. It is worth noting that the values of stress, especially the radial one, are significant and are really close to the yield strength of the material. To To conclude, I want to highlight some interesting points. First of all, the use of an uncoupled formulation gives great flexibility for this kind of simulations. Having an uncoupled formulation, it is possible to decopy thermal and mechanical analysis. In the thermal part, a constant initial temperature method is used. This model allows to set only one parameter in order to work properly. In the structural part, the representative welding process showed a greater accuracy than the classic method in describing relaxed strain results. The 3D numerical model, as well as the experimental data, highlighted that there is no clear axial symmetry in strain and stress results. Finally, residual stress results showed how the stress magnitude around the weld toe is significantly close to the yield strength. Thank you for your attention.